may seem like I'm dragging it out, but first of all, it's a long result, and we've done a lot of it very carefully, maybe more carefully than you want to see it. And as I promised last week, I'm outlining parts of it now, because some of the technique is a little repetitive. But there's one part of the technique that's new, and that I will do in detail. And then I'll show at the end of class how the higher wavelet is actually an MRA. Now that's not obvious, but so again, this seems like overkill because we proved the higher wavelet, the higher function gave rise to a wavelet basis, and I said inspired in that proof, which was very technical, you may recall, was the germ of the MRA. Then we did this MRA concept, which is quite beautiful. It, in some sense, combines coding from speech with this filter design stuff that we did, plus the pyramidal scheme coming from image processing. And we're in the middle of that proof right now. So when we finish that within the hour, then I'll show you how the higher wavelet gives rise to an MRA, which is not obvious. So somehow everything was circling around and making everything correct. And then we'll close out tonight by sort of odds and ends, which I think are interesting about MRA theory. Then next week, we shall do wavelet frames. And that will lead to, or can lead to, we won't have a chance to do it in this course, but something called generalized multi-resolution analysis, which in some sense combines, it's the big theory. It's not as big as the big theory, the final theory of physics would be, but it's the big theory in the sense that it combines MRA, but also non-MRA theory for sort of big wavelet theory. And then, the following week, something I like very much is wavelet packets. And Walsh functions are the primordial example of that. And the amazing thing is that there's still a lot of activity with Walsh functions. And so maybe I can give a hint of that. Okay, so the story of what we're going to do this week is the following. We'll as I said, prove the MRA theorem. Well, we've already done a lot of it, but I just want to remind you what we've done. And it's the following. So we already did the following in detail. One, given an MRA, Vj, we showed the following fact, that Vj plus 1 is equal to the orthogonal direct sum. We've got the little orthogonal sign here. They're not always orthogonal. The orthogonal direct sum. And not only that, and F belongs to Wj if and only if its dilate F of 2t belongs to Wj plus 1. Now, that's sort of interesting when you think of it geometrically, not to overkill here, but that is part of the MRA definition for the Vj's too. But the Vj's and the Wj's, you recall from that picture I showed last time, behave completely differently. Vj is contained in Vj plus 1, or an increasing or decreasing sequence of closed subspaces. Whereas the Wj's are all orthogonal to each other. And in fact, we're going to see that L2 of R is equal to the direct sum of all the Wj's. So it's sort of a fascinating little bit of geometry there. And a lot of these things, which are, we're going to prove, as I mentioned, for the dyadic case, are manufactured to work in a much more general case when for in RD for matrices that are more than just diagonal matrices and the like. Okay, so we already did that. The other thing we did, another thing we did, was by definition, phi minus 1, 0 is in v minus 1, and that's contained in v0. And not only that, what is this guy? This guy is 1 over the square root of 2, v of t over 2. And because it's in v0, that means we have the following decomposition: h0 t minus n. Oops. H0 of n over all the integers, and then phi of t minus n. Okay. And that's convergence in L2 of R. Where, and now that's just because we have an orthonormal basis. These translates are an orthonormal basis for v0, where h0 of n is contained in little L2 of z is defined by for every n in z, h0 of n is just the inner product. It's the Fourier coefficients, basically in Hilbert space, of the function itself, 2 to the minus 1/2 phi of t over 2, and then times the conjugate of the transient. And not only that, if I take the Fourier transform, so therefore, because of this formula here, we have that the square root of 2, p hat of 2 gamma, is equal to h0 of gamma, p hat of gamma, in L2 R, with R hat. Now, what we know is we proved that the H0 is a conjugate mirror filter. So, where H0 of gamma is equal to the sum H0 n e to the minus 2 I n gamma in L2 of R. But even though that converges in L2 of R, L2 of the torus, we know that H0 is a CMF. In particular, H0 is an L-infinity function. Now, there's a space that we're not going to study, but it's a very complicated space. When you look at the Fourier transforms of L-infinity, functions on the integers, but it's a very complicated set of functions on the integers. So you don't have to know this in any depth, but this sequence of Fourier coefficients of kappa equals 0 is a subset of so-called pseudo measures on the integers. Now, of course, that's contained in L2 of the integers, but still, it's not the sort of space you can intrinsically characterize in an elementary way. And so all of this stuff here is this whole technology that really, once you talk about having discrete subgroups of a group, then you can interplay Fourier series and Fourier transforms, and we're just doing what comes naturally in some sense. Okay. And then, after that, we stated the MRA theorem. So I won't repeat that, but in its abbreviated form, it says, given an MRA Bj phi, then there is a well-defined constructible function which we call a wavelet. There is psi depending, and it's constructible. Depending on the MRA such that this guy here, this sequence, is an orthonormal basis for L2 of I. Okay, so that's the big theorem we're aspiring to. Okay. Now, we've proved a lot of other things, okay? It's taking me a while, but you see it sort of in broad brushstrokes here. So proof. Now, I'm going to skip some things that are, I made some deals about last time, but just to keep my notation from the last time. So there was something A, which I'm not going to repeat, something B, which I'm not going to repeat. And then what we showed was that Ci, so we showed this, that a function f belongs to V1 if and only if f hat of gamma is equal to 1 over the square root of 2 v hat gamma over 2. F, depending on f of gamma over 2, where f sub f is a periodic function. Now, I've made a big deal on trying to be relatively careful about where the functions belong. But it was at this point last time that I pointed out that if you wanted this is where you have to make some assumptions on your MRA about your function phi, growth conditions, in order to say something about where this is. They're inextricably related interwoven. So if you have certain decay properties here, or sufficient decay properties here, you'll be able to say something about decay here, or that sort of thing. Okay? So there are interesting analytic problems to do at this point. And I mean, a lot of them have already been done. But there are interesting things still to do. Question? Is this what? What did I call it A last time? Yeah. Oh dear. So A is equal to CI, not CIA. Okay, let's call it CI today. Okay? Let me. And then C double I is V1 is equal to V0 orthogonal direct sum W0 and V0 perps W0. And we also proved C3 that for all of this part C, we have that F is in V1. And we prove that then F is in W0 if and only if we have this annihilation property, namely F hat of gamma plus K psi hat of, excuse me, phi hat of gamma plus K conjugate is equal to 0 everywhere. In using that, we can prove the following. Using C3, we have C4, namely, let F be in V1, then F belongs to W0 if and only if we have the following condition, which is a filter condition similar to CMF, namely F sub F H0 conjugate plus the translate by minus half of F sub F times the translate by minus a half of H0 conjugate is equal to 0 almost everywhere. Okay. Now, part D is, this is more or less where we ended. But, well, no, we did a couple other things, but before I talk anymore, I'm quite dry and get a last sip of water. Excuse me. So, okay, so from our filter discussion, and so from discussion of filters and the above, and admittedly, I'm being sloppy on these functions F sub F, except for the fact I'm asking to believe that I could straighten it all out with some analytic effort by making assumptions on the function phi and the MRA to begin with. So, from the discussion of filters and the above discussion analysis, if F is in V1, then F belongs to W0 if and only if F hat of gamma is equal to 1 over the square root of 2 phi hat of gamma over 2, and then K F sub F, the function K we spent a long time talking about, of gamma over 2, H0 of gamma over 2 plus a half conjugate, where and K FF is one periodic and we have that annihilation condition, namely K F sub So, with everything we've done so far, this is where we are. And I think you can believe that you can pull all that stuff together. Now, let's call this DI. Now D double I. For any one periodic function K, define function L of gamma to be equal to e to the minus I gamma K of gamma over 2. Okay, I'll run out of letters pretty soon. Well, I still have a few. Then we can assert, and I'll skip the details, it's easy. Then L is one periodic if and only if K of gamma plus K of gamma plus a half is equal to 0 almost everywhere. This is more or less a technical convenience, but it does look pretty. And so then we can combine all this stuff along when functions in V1 are in W0, or I'll call that D triple I. And it says that let f be in V1, then f is in W0 if and only if f hat of gamma is equal to 1 over the square root of 2 d hat of gamma over 2 e I gamma L f of gamma H0 of gamma over 2 plus a half quantity. Okay. Now, may not look pretty, but very explicit. And we can say where LF is 1 periodic. So this is a heck of a result if you think about it. It's saying that if we take a function in V1, well, what it's saying is by the MRA, we've got a phi and we've got the H0, and we're saying that that right-hand side is in W0 for any one periodic function. It's characterizing belonging to W0. And so, let's start with another letter of the alphabet. E, I. So, it's uncool to go up to I, so who knows what's going to happen. So the key feature of the MRA algorithm is that, so a key feature of the MRA algorithm, I mean, it's really a theorem when I say the right things about where phi is, but the right theorem. Correct hypotheses of phi. construct psi in W0 such that R and psi is an orthonormal basis for W0. Well, to this end, define to this end, define psi hat of gamma. I'm just going to take a simple L here, like 1. What the L? Funny at all, it wasn't even like real thing. So, define 1 over the square root of 2 p hat of gamma over 2 e to the pi I gamma h0 of gamma over 2 plus a hat conjugate. And we note in particular that this belongs to L2 of our hat, since h0 is an L infinity. Okay, I'd like to make an interlude here. I'd like to ask the question, in light of what I'm about to prove. Why don't you write this down as one of the exercises? Find MRAs, let's say construct them, write them down, such that psi, let's call this star, defined by star does not give rise to an orthonormal basis for W0. That is, R and psi is not an orthonormal basis for W0. Okay, so because this is essentially the algorithm, not worrying about my hypotheses on psi, but if I have an MRA and I write down psi or psi hat, I write down psi hat this way, then I'm going to be able to, in general, or most of the time, write down an orthonormal basis for all of L2 of R by the size of MS. So if you just forgot about the hypotheses I said I needed on the feed to have things work, if I can say that this is in W0 or something like that, do I always get an orthonormal basis for W0? That's our question. Okay. Now, so this is EI. We're going to prove, well, again, I'm going to sketch, it's all sketch, but because we really have done a lot of details in the classes, that this does give an orthonormal basis for L2, for W0. So E2. F in W0 implies that F is equal to write it down as a sum of translates of size is equal to the sum C N F tau and psi in L2 of I. Now here again, I'm assuming my math is correct. I'm assuming I have an MRA and that I can say the right things about the capital F sub F. And basically, without, again, not doing the details, what we have is we go over here, and that's a one periodic function. I write out its Fourier series, okay? And by the way I've defined this, what I have is I've got psi hat times that Fourier series. Okay? So I've got that F hat is equal to psi hat times the Fourier series. And then I just use the Fourier inversion formula, and I get this. So I really am combining, this follows by Fourier inversion. And if this is star, I guess this is star stuff or something. So it follows, this follows by Fourier inversion and star. Okay, everyone understand what I just did then? All I did was look at star sub F. L sub F is one periodic. I write out its Fourier series. So that means I can write out star sub F as psi hat times that Fourier series. And then I just, which means I'm looking at a sum of coefficients times this guy times its exponential. And the inverse Fourier transform of that is just psi of t minus f times those Fourier coefficients. Okay, so if f is in W0, then I can write down f in this way where we find the correct hypothesis of a phi. These CNs are in L2. Okay. And then E3 is I have to show orthonormality. I have to, we shall have proved tau and psi is an orthonormal basis. Orthonormal basis for W0 once we show, once we prove that these guys are orthonormal. Right? Everyone on board with that? Basically, we'll have this as orthonormal, and all I need, I don't even need this strength, all I need is that they're dense and I'm getting decompositions. But once they're orthonormal, it's an orthonormal basis by the sort of that basic Hilbert space theory that Enrico showed you several times ago. And to this end, we just make a calculation to do this. We calculate look at the integral of psi of t minus m. I'm not going to do all these details since we did a very similar calculation for the fees. T of psi of t minus m, psi of t minus n conjugate. And then you can almost see it there. So it's beginning to be looked at. That basically we can write this down that as an integral from 0 to 1, this is over I, of a capital psi, okay, of gamma, e to the 2 I n minus m gamma, e gamma, where this guy here is equal to the sum of psi hat of gamma plus k quantity squared. Right? Because here, I mean, this is the calculation we've done before. Along for all of R, I write this down then as the by Plancherel as the integral over R hat of psi hat of gamma absolute value squared, okay, times the this exponential here, and then since I'm summing over all of R hat, then I split it up as over sums of intervals of length 1, and that's what that is. And then once I have that, we know that psi, the capital psi, is in L1, and we are going to be able to, we obtain orthogonality once we show the capital psi is identically, is the function that's identical. So we obtain orthonormal once we show capital psi is identically 1, 0, 1. And we've already done that too, but we did it for capital phi. Basically, we just write out what capital psi is. In fact, capital psi of gamma, and I just write it out. I've got to split it into looking at the sum over odd and even integers. So k equals 2m plus k equals 2m plus 1, and the stuff inside is 1/2 of phi hat of gamma over 2 plus k over 2, and then times the h0 term. So h0 gamma plus 1 over 2, oops, we got k, plus k. Okay, we did something very similar to that earlier, and then when you just write this out, you get this is equal to 1, because we're dealing with a conjugate verifiable. So this is equal to 1 since h0 is a conjugate verifiable. So by skipping all the steps, which I'm doing now, you're all relatively awake. On the other hand, it probably sounds like I'm lying to you once in a while. And on the third hand, I'm making fewer mistakes than the blackboard. But basically, so this is the capital psi. I just wrote this down in terms of the psi hats. I looked at what psi hat was over here. Okay? And I get this term here, and I split it up into odd and even parts. And by the same argument I used when I did something earlier, by splitting it up into odd and even parts, I can then using the fact that it's a quadrature filter, I get the thing equal to 1. Okay, so we have ourselves a orthonormal basis for W0. Now the next step is the following, so I'll call it E5, E4. And we're going to keep our eye on the side over there. And by the way, the reason I pose this question is that basically this thing is an algorithm in the sense that we, even in the cases we don't take the right fees, we see how every step is somehow meaningful if you have the right hypotheses. And so in the process we come up with a formula to make them. So I mean that's really the basis of what I mean by algorithm in this case. We come up with a formula that is very reasonable if we put the right hypotheses on the field. Okay, so here we are, for we shall write star as, and let me bring it over the other side since I want to have it in an analogy with what we did for phi hat. So we have square root of 2 phi hat, excuse me, psi hat. Psi hat of 2 gamma. So I brought the square root of 2 over the other side, and I'm replacing the gamma by 2 gammas here. Okay? That's all I'm doing. And that's going to be, we're going to call it phi hat of gamma. And then I've got all this other stuff, including that exponential and the H0, but I'm going to call that H1 of gamma. And I'm just rewriting star that way. In L2 of R, where, and now let's write what H1 is, where H1 of gamma is equal to e to the pi I gamma. Excuse me, I have to put a 2 in there since I multiplied. E to the 2 pi I gamma H0 of gamma plus a half conjugate. And then if I do that, I mean, just by the way I've got things set up here, sometimes you see the pi's and things a little bit differently. But by the way I've got things set up here, where H1 is this, and its Fourier coefficients are H1 of n is equal to minus 1 to the n plus 1, and then H0 of minus n minus 1 conjugate. Okay. And you can see how all that's going to be playing out just because of this way we're defining it. We've got to translate here, we stick it in there, and so that's all coming out. And where you can also say that psi of t is equal to the sum h1 of n square root of 2 phi of 2t minus n. Okay. So all I've done is, I mean, I have omitted some of the grubby details here, but I've rewritten star in a way that was very similar to the way we wrote phi hat, but now I have a different filter here. And that filter arises because of this guy here, which arose in a natural way for characterizing W0. And then, since I know what H0 is, then I can say what H1 is in terms of the Fourier coefficients little h1 this way. And so this formula here is just the Fourier transform of this formula is just this. Okay. So I have just, I'm just playing games with taking Fourier transforms. But everything's correct. Given an MRA where from that very first step I have the capital F sub F being in a good space like L2. Okay, so we've written what capital stars. Now, the next step, some people view the next couple of steps as very easy. I mean, they sort of see it. I remember once watching Willie Moscone, who I don't believe was he may have been a proud man, but he wasn't braggadocious. Probably the greatest pocket pool player ever. Although nowadays, I haven't followed it carefully in recent years. But if you're playing straight pool, and then you reach a stage where you only need to sink 10 more balls and they're all sort of spread out on the table, you don't have to be subtle or anything. If you're talented, you just sink them. And I think the people who do wavelet theory who say, well, then the rest is obvious, that's the analogy, because at this point they say, well, it's all done. But slow and steady wins the race, so you're going to get it slow and steady. So we move on. So the first thing is, we're getting eerily close to II, but
Starting with alpha.
that's right, I'll have to Greek or Swahili or something. Well, we have several Orientals in the class that can help me out. Who knows? So F. So recall F is in W0 if and only if F 2T is in W1. So define the mapping. So the mapping dm from W0 into Wm defined by the action d of psi 0 n, dm of it will be psi mn. Okay, and I can define that overall W0. Well, I define it by that action. It turns out that's an isometry. Is an isometry. Includes an isometric projection. And so therefore, without doing any hard work, therefore psi mn, as I range over all n's, is an orthonormal basis for Wm. So now we're going to go to G. So G dot I. So from the definition of an MRA, if J is less than M, then WJ perps WM. And why is that? Well, Wj, why? And the answer is not why not. Why? Well, Wj is contained in Bj plus 1. And that's contained in Bj plus 2 all the way up to Bm. And what do we know about Vm vis-a-vis Wm? We know that they perp each other. But Vm perps W. So therefore, Wj perps Wm. So maybe I shouldn't be repetitive here, but that picture I drew last time is a little telling, in the sense that we had V0, and then we had, by definition of an array, V1, and then we define W0, and then since we have V1 contained in V2, V2, okay, remnants of Pinamundi. That's where they made Pinamundi is where they make the V2 rockets during World War II. And so we know that then we define W1. Et cetera, et cetera, et cetera. And so, so this is increasing forever, but also decreasing forever. That V0 breaks down into two subspaces, V minus 1 and W minus 1. And there's this remarkable book, which was made into a movie called Powers of 10 and Powers of 2. And it begins sort of, I don't know, Central Park or something. Expand up, and you goes this way. You're dealing with Sirius, and then you're goes down, so you're dealing with micro Sirius. Okay. Now, I talked earlier about the orthogonal direct sum. Let's just talk about direct sums for a moment, which is why I put a perp on it earlier tonight. So, my time doing this. It'd be nice to finish this before we take a break. If we can last through. So this is just a little aside for definition. We can state it rather generally for topological vector spaces, but let me just state it for product spaces. So definition, let U M into Z be sequence of closed linear subspaces of a Banach space B, and let X be equal to the set of all functions f of the form finite sum of f m's belong to, now I use capital F sub F, I'm going to use F of F here. It's going to be finite sum is the key thing. So Fm belongs to Um, and F of F is a finite set of integers. Okay, so I'm looking at all those finite sums. And so this is really just a definition. X is the direct sum. Not worrying about orthogonality or anything like that. Is the direct sum of the spaces U M. And we write down written X is equal to Um if we have a unique representation. Okay? If each element of X has a unique representation in terms of one. Now, you may recall in our definition of multi-resolution analysis, we have used the fact of the orthonormal basis that translates to V0, and we have used the fact that F belongs to Vj if only if F2t belongs to V j plus 1. We have not used the union of the Vj's being dense in L2, nor the intersection of the Vj's being 0. And so at this stage of the proof, we shall use those facts. Okay. So G2, so that's now G2, I think I'll use a piece of chalk, it's going to be small. Okay, so that the sum Fm equal to the sum Gm, where Fm and Gm are in Wm. So I'm going to really make use of the fact here that these guys have only the 0 element in common, okay? As opposed to the V's, which are included in each other. Where Fm, Gm are in that, and all but finitely many are 0. Each is 0. Well then, what can I say? I can say that for all M, I look at the sum over all the j's that are not equal to a fixed M there of Gj minus Fj, and that's equal to Fm minus Gm. Okay? And that belongs to, since Wm is a linear subspace, belongs to Wm. fun by comparison with some of the onerous calculations we did past two. And so therefore, if I look at Fm minus Gm in L2 norm squared, then I'm just looking at the inner product of this with itself. And that, excuse me, if I take that with that, so I'm looking at the inner product of this with itself, then what I have is I have this being the sum J not equal to M of Gj minus Fj Fm minus Gm. And of course we've already ascertained that the Wj's perp the Wm's, and so this is equal to 0. And so therefore Fm is equal to Gm, and so therefore this set here of all f's which are finite sums, we're looking at m's in some finite set of fm's where the fm's are in Wm. That is the direct sum of the W's. Okay? So, easy algebra, but why not do it? Okay, so now we're moving on to H because we want to get to the conundrum of II. So, for H, by definition, every integer cap j the closure, I'm just going to write down the definition of closure. From j equals minus infinity to cap j closed of the Wj's. What does that mean? Well, this is going to be the set. It's obviously contained in L2. It's going to be the set of all functions f in L2 of R. And I keep reminding you, because I think it's exciting, because you can see that we're doing so many things that we can just generalize if we wanted to, if we wanted to use one chart. And so, I mean, that's one of the beauties of this. So, set of all functions in L2 of R, which such that for every epsilon bigger than 0, there exists a G epsilon in the actual algebraic direct sum j equals minus infinity up to j of the Wj's such that f minus g epsilon is less than epsilon. Okay, so I just wrote down the definition of closure because we're going to use it. Okay, so once again, with poor blackboard spacing, let's go over here. So we shall prove, by the way, since some of the details are routine, I really will sketch today, as I promised. We shall prove that the direct sum closed from j equals minus infinity to j of the Wj's is equal to Well, what do you think it's equal to? If I am in V0, if capital J is equal to 0, and then I do my powers of 2 downwards, okay? I'm sorry? Well, it's going to be equal to Vj plus 1. Because basically, I'm going to, I've got all these W's, and I'm going to go down here to, well, just keep going down. So this, we suspect, is equal to Vj. And it is. Say that again? V0. I heard the word V0. What else are you saying now? I'm sorry, I don't understand your question. That's my problem. Is V0? So all I said was, if I go to 0 here, the W zeros, then, oh, I say, you're saying I don't have, good point. I don't, do I get V1? Well, W0, and so W minus 1, you see, is where? It's in there. And that's the reason I'm going to pick up all of V0. So that's the reason I get all of V1. I mean, that's a very good question. That's exactly the reason. That's exactly the reason. Okay, well, this is clear. Because of how we define things. I mean, the direct sum. That is clear. Because W, since I take any Wj, that's contained in Vj plus 1. And that's contained in all the way up to taking all these j's, you see, up to j, so that's contained all the way up into Vj plus 1. So, for all j less than or equal to. And so, basically, finite linear combinations of the different Vj's are also Vj plus 1. So therefore, finite linear combinations of elements from the Wj, j less than or equal to 1, are in Vj plus 1. And so therefore, the direct sum is therefore the direct sum from j equals minus infinity to cap j of the Wj's is contained in Vj. Okay, so that inclusion is clear. And the now let's take an element here and get it in there. So let's call call this H, I have H3 yet? H3. That F, B, and V, J plus 1.
I think it's H2.
What is it?
H2.
You're right. But I wrote H3 here, and I'll get so confused if I change it. So let's take an H2 here, say. Okay? Thank you, Bob. Things like that bring me to a screeching halt. So let F be in Vj plus 1. And, well, what does that mean? That means we can write down F, therefore, F is equal to Fj plus Gj, where Fj is in cap Vj and Gj is in cap Wj. And since we do have, this is Vj is, that's an orthogonal direct sum, with Vj and Wj being Vj plus 1. We have, therefore, the norm of F in L2 squared is equal to Fj in L2 squared, with the Pythagorean theorem, plus Gj squared. And that follows since Fj Gj is equal to 0, right? I mean, I just look at right? Right. We do everything. We do really simple stuff, and so we're good to go. Okay. But now let's continue that game. So now let's write F similarly. I'm going to write down Fj. Fj is in Vj. And so I'm going to go down 1, Vj minus 1, and Wj minus 1. So similarly, F is equal to Fj minus 1 plus Gj minus 1 plus Gj. And once again, if I just look at the L2 norm of that Fj, I'm going to be able to say that therefore the L2 norm of F squared is equal to Fj minus 1 squared plus Gj minus 1 squared plus Gj squared. Why not? And we continue that way, and we have that for all m less than or equal to cap j, f is going to be equal to fm plus the sum of gj's, j equal to m up to capital J, and we have that the norm of f squared is equal to the norm of f sub m squared plus the sum of the gj's squared, where j goes from m up to capital J. Everyone agree with that? And of course the fm's, just to write the complete fm is in vm, and gj is in wj. Now, if I look at these sums here, they're going to converge. I'll show you why. So note that the sum of the GMs, or I'm using J equals minus infinity up to capital J is equal to some function G in L2 of our topology for some G in L2 of R. And why does that hold? That holds because I'm going to write down the sum Gj, J equals minus infinity to J, is going to be equal to the sum of the norms of the GJs in L2 norm times the HJ. I'm going from J equals minus infinity to cap J, where HJ is equal to GJ over GJ in L2 norm. Okay, what does that prove? Well, that converges because the GJs are in WJs. The WJs are all orthogonal to each other. And now I've got an orthonormal set here. Okay? So it converges in L2 of R, since the set of HJs are orthonormal, okay? And the sum of the norms of the GJs squared from minus infinity to J is less than infinity. Hark! Why does that hold? Well, that holds because of this. That right-hand side is non-negative and bigger than that. And that's finite. Okay. So this is less than infinity by maybe another startup number here, 2. Right. Okay. And then, okay, let's see where we are now. We have an element in Vj plus 1, and we have it. We can write it down in this way, and in the limit, we've got that the GJs converge, and so note that, well, where does G belong? G is in the closure of the direct sum. It belongs to this guy here, J equals minus infinity. And I mean, the reason that holds is that if you take any fixed M here, the finite sum of the GJs belongs to that without the closure, and then it just closes. Oh, yeah, J. Right. So what do we have to prove? Thus, the inclusion here, wherever I am, will be done. Excuse me. Thus the inclusion will follow. Once we show that f is equal to g, and I've taken f in vj plus 1, and if I can show that f is equal to g, so this will follow once we show f is equal to g. And this is where we use the key property of an MRA, that the intersection is 0. So for this, we use the MRA hypothesis that the intersection of all the VJs is the 0 element. And we use that in conjunction with 3. So for this, we use 3. And now, this is one of those details I'm going to skip. I mean, it's done here, but it takes a while. But you can see what's going on. Basically, you just have to show that the FMs are going to go to 0, and they do. It's just a matter of doing the inclusions correct. So, easy. Longish maybe details. But you see the idea. It's really cute. Okay. Now, we come to the magical moment, I. So, and I could have had an I sub I, but I decided just to have one I. So, let's go with this end. So we've done that, and now we can now verify I. We can now verify that this guy here, all the WMs, all closed up, is equal to L2 of R. And basically, we use our other key property of MRAs, namely that the union of the VJs is everything. So let F be in L2 of R, and let epsilon be bigger than 0. By MRA property, by MRA definition, there is a G in the union of the VJs such that F minus G is less than epsilon. So that means it's in one of the VJs. So suppose G belongs to Vj plus 1. We're almost there, right? It belongs to Vj plus 1. Then by part H there exists GM M less than or equal to J, all M less than or equal to J. And there exists some constant M epsilon bigger than 0, such that for all capital M bigger than or equal to capital M epsilon, G, which is in Bj, minus M from minus capital M to capital J over GMs less than epsilon over 2. And we're done. We're not 100% done, but we've finished this part. We've verified that that's true. And then the final thing for this is we wanted to show that finally J finally prove that psi Mn is an orthonormal basis for L2. Well, basically what we know is that it's orthonormal. We've done that because each of the, for every fixed M, psi Mn is orthonormal inside Wm. And so, and each of the Wj's and Wm's is orthonormal when J is not equal to M. So psi Mn is orthonormal since for each fixed M psi Mn is orthonormal, and Wj, we already proved, perps Wm if J is not equal. And so all we have to do is to therefore need only show that the sum of the psi mn's spans L2 of I. And that is to say the closed linear span of the psi mn is equal to L2 of I. And what do we use for that? This follows from I. This is a consequence of part I, which involves a calculation, but again, it's just doing epsilonics this way. By epsilonics. Okay, so I think you've seen a very honest proof of this result. And it took a while to finish this off, and I left out a lot of these details. Let's take 5 minutes. Oh, before I do, 1 second, Brendan, because my brain's like a sieve. There's a wonderful article. It was wonderful since it was so timely, and I was certainly asking these questions myself, but never, probably couldn't have done it, but certainly didn't do it. Wally Maddich. And it's in a book on, in the article, in book, edited by Charles Chewy. He's one of the major players of Wavelet theory. The book is from 1992. And it has one of those titles that we were giving books in those days, something like Wavelet's Tutorial in Math and Applications. It has a colon and then some other words. But the article by Maddich takes a very critical look at the hypotheses for a multi-resolution analysis, and they are not independent. Some follow from the other, and I've forgotten off the top of my head what they are. But if someone wanted to write their report on that article, I think it's a great article. Even though it's old by Wavelet standards, it's a very interesting article. And again, I think that's the sort of article that's from which other ideas can come for more general situations. Brent, your comment?
Yeah, you had kind of hinted a number of places there were additional conditions on the MRA that were necessary to clean this up, basically?
Yeah, basically on the function phi.
Okay. Do you have a reference that would go through those details?
Oh. Well, so first of all, I've got them in my own notes, but the major, which are not ready for viewing by the public, because they're really messy, but certainly the basic books have some of these facts that they tend not to put in the detail that I put in. So the book by Yves Meyer from 1990 lays on to that, certainly has the results. The article by Malat in the transactions of the AMS in 1989 has those results. That's actually a nice place to read it.
Okay.
Malat's article, Meyer's article from his lectures in Torino in 1987 has them. Dobeshi's book from 1992, 10 lectures, has them. And I must say, I mean, I learned my Wavelet theory from that period of time, so maybe more recent books have them. I just don't have that information about the literature at the top. 5-minute break?